In this lecture, we're going to look at the direct boundary element method for acoustics. You've already seen the finite element method, and I consider that to be perhaps the easiest way to learn about acoustics. But when you have infinite domains, then it's better to go to surface-described acoustic situations where you can put sources on a surface of a vibrating body and then see how that information is moved out into the space. Now, the direct method is one where the source is presumed to radiate in essentially one direction only, on one side of a given surface. Then we have to define a normal to that surface to say which side we're interested in, and in our theory we'll take the normal to be positive when it's directed away from the volume of interest. When we get done, we'll look at the fundamental solution in a small problem in our small problem session at the end. Let's now sketch a vibrating body and consider the acoustic field that could either be surrounding it on the outside or contained within the vibrating surface. When I show this sketch as a two-dimensional cut, I really mean a potato-shaped body that's containing some volume in a three-dimensional space. We would have that dividing surface shown by the solid line here, and then notice that I'm showing vibrations that in physical nature would actually both be going outward and inward. The method we're going to use here, called the direct method, will only consider one of those directions. We're going to need to look at points on that vibrating surface, and these are basically the sources of the noise, and then we're going to need to look at remote points either outside the body or inside it if you're interested in the cavity, that are going to be data recovery points where you're interested in the sound pressure level, let's say. The dark symbol R is a radius vector, and the R subscript data recovery is the viewing point that we're interested in. Now, many times these remote viewing points are clustered with a number of such points into perhaps a planar viewing surface here or a spherical viewing surface around the body. It's possible to automate that recovery of data so that the user can then present a rather nice graphics figure of the sound pressure levels at this remote viewing surface. Now, the points of interest for sound measurement might as well be on the inside, so we will consider the general case where you might be interested in either the outside or the inside of this body. For instance, an automobile passenger cabin would be in the inside of the vibrating shell that is the body of the automobile. In our earlier lectures, we've shown that the governing differential equation is called Helmholtz equation, and it's proposed for a harmonically oscillating pressure field due to various moving surfaces that cause noise. Helmholtz equation on the left here is often zero in a free field, but if you have a point in the field that's causing either a disturbance at point R or the measured point here at the data recovery surface, then there will be such a delta function. So in your mind, interestingly, although the subscripting here is a little bit awkward, you might think of this data recovery surface as the independent variable here, and this point on it, and then refer to the point where the source is. I think that this can be a little troublesome at the outset. Later we're going to sum over all of the sources, and many of you would be more used to seeing the independent variable not be subscripted and the other one to be independent, but in this case it will be the other way around. It's been shown that the fundamental solution for the operator on the left here, when it's homogeneous, that is when there's zero on the right, is the so-called fundamental solution with this radial character. K again is this wave number, which involves the frequency of oscillation, and then this absolute value gives the absolute distance between the viewing point and the source point. So in 3 dimensions then, you have the signal dying out in strength as you go out to larger radius, and varying as 1 over the radial distance, basically. That means that the energy involved then will have something to do with the surface area involved and the intensity of the wave moving outward. The 3-dimensional pressure field, if we go back to our Helmholtz equation, you see we've really taken the time dependence out of this. And if we put that back in the form of this general functional expression, then we need the fundamental solution in space as well as bringing back in this time dependence. Equation number 1 that we showed in the previous figure is the non-homogeneous equation that holds throughout the volume of space that we're interested in. The driving force is this Dirac delta function that shows the effect of a source at a general point R. Our approach will be to integrate that non-homogeneous equation over the volume of interest. And we'll be getting contributions from the locations of all the sources on the moving surface. I've repeated the equation here, and I want to do kind of a trick then and pre-multiply this equation by one or the other of the terms in the Helmholtz equation itself up here. This is the homogeneous form of the equation, and I use a general pressure P in that case. This non-homogeneous form here has a Dirac delta function on the right, and then I use a special symbol for the pressure that we've previously called the fundamental solution, this psi. Now both psi and P are pressures, but the ones above I'm going to use in a sort of a weighting function way. I'm going to carry one or the other of these terms in this upper equation and color them red and multiply in turn the terms in the equation here. So first of all, I use minus k squared p on the del squared psi term. Then I use the del squared p on the psi term. Then I use the minus k squared p again on the Dirac delta function. So it's pretty easy to see how we're doing it. Let's see, I can say that I've taken this term over here and here, and then I've multiplied this term times this one. Now, if I rearrange and then if I show the coordinates involved, we have this equation. What we're going to be doing basically is integrating over the position of the sources, which is the R vectors, and thinking of the viewing point in this case as being held constant. There's a kind of an interesting form here if you're familiar with the vector integral theorems, where you have a function here times the second derivative of another function, and then the reverse. You have the second function without a derivative and the first function with the second derivative. So there's a kind of a nice symmetric form there. So now we carry out the integration over the volume of interest. And this could either be the interior cavity in a shell-like body, or it could be the exterior field around a vibrating body. So this volume integration means to integrate over the volume V, whichever case that we're speaking of. And then the table below will show what happens to this Dirac delta function times the pressure depending on your location with respect to that. And you'll find that when you integrate over the volume, if this Dirac delta function lies in the space that you're interested in, let's suppose you're interested in the external field in red here, and I've kind of truncated it because I can't carry it to infinity. But okay, suppose your volume is here. Then if the recovery point that you're interested in lies in that volume, you're going to get a value from this integral that will recover the pressure at the viewing point. If your viewing point moves on to the surface itself, it turns out you get this quantity of 1/2 times the pressure there. And lastly, if your data recovery point's on the inside, in this case where you're really interested in the outside, then you get 0 for that right-hand side of the equation. Each of those quantities would be reversed then in the case you were interested on the inside region. And so I've made a table here where V is the region of interest, and then you have to interpret this whether you are in your region of interest or not. That symmetric form that we had with second-order operators in it can better be replaced by different formulation, primarily if you can reduce it to first-order derivatives. This allows you to have a little bit better handle on the continuity of the field between the elements and requires less in the way of continuity. It's one of the things that's done often in these integral formulations, is to try to reduce the order of derivatives that you have to evaluate. You know that integration is a smoothing process, but differentiation you might call a roughing up process. So the symmetric form that we had, which was on the left side of our non-homogeneous Helmholtz equation, is going to be replaced by this. So this is actually an identity, and the second derivative here and the second derivative here now will become first derivatives. In fact, there are normals evaluated on normals to the surface involved. And this surface that you're interested in might include not only the finite surface of the vibrating body, but it also would, if you were interested in the exterior problem, include the boundary at infinity, and that's what the capital sigma means. So for that case where the volume of integration is the exterior problem, then you're going to need both of these symbols here. Interestingly, we're going to show in a minute, though, that the quantity to be integrated on this far field, this exterior boundary at infinity, goes to 0. So although we've put it in, we luck out at that point. Now, we have to take then this form of our symmetric functional up above and then set it equal to the right-hand side where the Dirac delta functions occurred, and you'll see that in the next figure. In the method that we're using, the pressure at the surface and the velocity, the normal velocity of the fluid next to that surface, are the important variables. So these are physical variables that are fairly easy to comprehend and leads to this idea of a direct boundary element method. So that's what I comment in the first sentence, and then we distinguish between the exterior field, which is considered a radiation problem, and then the interior field where you only have the volume of interest inside some kind of a vibrating body, as in the case of the automobile body cabin. And here I tell about the radiation problem, and because of the Sommerfeld radiation condition, the fact that that integration over that far boundary, which is infinitely large, is 0. It's a little bit physically inclined as well. Sommerfeld's original argument was that if waves were going outward, they wouldn't reflect back in, and therefore you want to eliminate the possibility of inward traveling waves when you have the full radiation problem. Now for the interior problem, then you never had that surface at infinity. You only needed the integral over S. So it turns out that actually whether you're doing the interior or the exterior problem, you get the same kind of an equation form here integrated over this finite body surface. But then you have to adjust this coefficient on the right to tell whether your viewing point lies inside the acoustic domain that you're interested in, that volume, or whether it's on the other side of the dividing surface. And so you get these different permutations that we discussed before. What we're trying to do here is develop a set of equations in the unknowns, and hopefully we're going to end up with n equations in n unknowns. The integration that we've talked about was originally a volume integration. Then we changed it to a surface integration by using the vector calculus ideas. At some point now we have to learn how to sum over all of the sources on that vibrating surface. So that will be the next sketch. Arbitrarily, let's suppose that we're looking at an interior point to an egg-shaped body. And by cutting the body, I'm showing the shell here, and this data recovery point is felt to be on the inside of that body. So it's going to be, I'm going to have to imagine the body originally came out here some distance, but was then cut. Then what we need to do is to do an integration with this point fixed, but then find out what all the sources are doing that lie on this vibrating surface, and then are projecting acoustic waves to the interior of this cavity. Let me review the choices for that constant C that tells whether your viewing point is inside the cavity or outside. When the viewing point or data recovery point is on the inside of this cavity, then the constant C is a unit value. The normal is positive when directed away from the volume of interest. Then what you're trying to do is integrate over surface elements such as shown here, this red surface or this one here. If the data recovery point is to the outside of the cavity in question, then the constant is 0. If the data recovery point is on the surface, then the evaluation is done with a constant C of 1/2. The normal again outward here, and it will turn out numerically that that there will be n such source points around the body when we go to our numerical integration. And so we must consider those all around the surface of the body in question. Likewise, for the exterior problem, you have the same combinations. In this case, though, if it's the exterior field that you're really interested in, when you have a data recovery point on the inside of the cavity, then the multiplying coefficient is 0. Notice that the positive direction here is inward. When you're on the outside of the cavity and you really are interested in the exterior problem, then your coefficient is unity. This vector then pointing away from the exterior field. Finally, if you have a data recovery point on the surface of the vibrating body, then the coefficient here is 1/2. I've alluded to the fact that we're going to end up with n equations in n unknowns, but really that's a part of what's called discretization, and we'll do that in a formal way now. We need to sum over the sources that are located on the vibrating surface. This becomes a surface integral. Therefore, we only need to create surface elements in the boundary element method. This is a great source of efficiency now because you only need to mesh a surface rather than a solid volume. That's an easier process. so that it is therefore labor saving. There are times when it involves more computer time because the equations that we get ultimately, even though they're smaller in number, can be fully populated. In other words, the coefficient matrices are full matrices rather than strongly banded as in a finite element problem in a volumetric space. So I think that's the trade-off we're going to have here. We're going to reduce the labor and then yet have a set of equations that are fully coupled on the given space. When we start this discretization, then, we're interested in triangular elements and quadrilateral elements. Here I'm showing those elements as mapped upon a two-dimensional C1, C2 space, and I've already shown what's called the parent element here, which is square. Think of it as a double unit square. So that if I had, as shown below here, a proposed triangular element and next to it a proposed quadrilateral element, they would look like this. Let's look at the isoparametric formulation now for setting up these surface elements. First, we interpolate the pressure field, and we use the two-dimensional shape functions here, the n's, and use the nodal values of pressure P superscript m. Now there are as many as capital M nodes in question, and so we need to sum this for the given element. The isoparametric concept is that you use these same shape functions to interpolate the element geometry and in particular the boundaries, and so those same shape functions show up below. The same shape functions can be used in each of the three dimensions and multiplied by the coordinates at the nodes. This is indeed a mapping, though, from a two-dimensional space into this three-dimensional physical space, so it's not trivial. Luckily, this is easy to do in computer implementation, and I think that in spite of the apparent ferociousness of the theory, it turns out in practice that isoparametric elements are easier to implement in a computer code than a person might think. Now let's see if we can set up our n equations in n unknowns. In our direct method, we only need one boundary variable to be specified at a boundary, and then we can solve for the other. We're going to locate a data recovery point on each one of the nodes and leading to n equations shown below. So J would be the number of data recovery points here, R sub j. R, remember, is the location of the source points, and so we now have a balance of n source points where the pressure disturbance is located, and then we're looking at the pressure and recovering it at n node points. So we'll get n equations in n unknowns. I've got another index, capital I, illustrating the total number of elements, and I'll show some of that in the next figure. Let's look at our interior problem as an example and set a data recovery point, and then look at the vibrating wall of the shell that we're trying to cope with. So here's the body that's shaking away over here, and our data recovery point might be here. What we mean by R1 would be that here is a distance to the to this node R1. Then, in like turn, we could look at the other nodes, of course. In this case, each element has 4 nodes because I'm using quadrilaterals. And then the element number itself, I'm drawing as small subsurfaces, S1, 2, 3, and so on. And so obviously you have to sum over all of the nodes involved. The acoustic equation started out as a volume integral. Then through a Green's formula we turned it into a surface integral. Now we'd like to change that into the local surface coordinates C1, C2 that are defined in each element. Such a change of variable would be shown here. The Jacobian is the area ratio that takes into account the different scale of the C1, C2 variables compared with the original physical variables. Note that each one of these integrals here involves a quantity in the pressure field, which is the field variable, and here are derivatives of it, and here's the pressure field itself. And then those multiply these fundamental solutions here, which are our reference solutions, which are known. So the unknowns in this equation would be involved in these leading terms here, either this gradient of pressure, which is velocity, or the pressure itself here. Now, at each grid point then, or each nodal point, we have to specify either the pressure or the velocity. These terms are superscripted to show m as the value of the node in the element, and then I is the element concerned. Ultimately, you have to sum over all the elements and nodes in the problem. Let's consider this pressure gradient in more detail. dP dN means the change of pressure in the normal direction at a surface. Mathematically, you can take the gradient of the pressure then in a space and then do the inner product with the normal of the surface. Gradient of pressure we can show is related here to the velocity, and we still have the vector velocity and the normal involved. This normal should be known for your given situation. Now, the importance here is that we have to specify boundary conditions, and we need one condition at every node. This is similar to the finite element theory, where at a node you must either specify the field variable or a gradient of a field variable. In this case, pressure and velocity are reasonably straightforward. You can also have a combination where you have an impedance at a surface, perhaps due to some kind of absorbing surface. And then you can get a combination of simultaneous velocity and impedance. Sometimes it's possible to have a padded surface where the velocity has been given as an input, and so the combination is specified. Let's consider the multi-zone concept. Sometimes in a problem you have an internal fluid interface, such as the interface between the gasoline in a fuel tank with the air above the fuel. That sketched here is this potato-shaped body with a region Sj, which would be air perhaps, and then a region Sk that would be the fuel. Then this interface between would be a real interface in which you'd have to separate the material properties in the two regions and make sure that they had proper speeds of sound, densities, and so on. The interior problem we're solving here then would consider what would happen as the shell-like structure around this were vibrating. In the multi-zone concept, you identify the intermediate region, the fluid interface, as a region S sub C. I guess you could think of that as a common boundary. And that has to be meshed as shown in the right. So now you have to mesh the this interface zone as well as the wetted surfaces around the periphery. Let me suggest how the mathematics might look then when you do this block bandedness process. Here I write out the equations for each region separately, and in each case we're going to number the common degrees of freedom with the subscript C, and here we have pressures and velocities appearing. So this would be the region for the J fluid area. Then the K fluid area also has these same velocities and pressures that are common with those above. So it's possible, and you can do this in a few minutes to show that this is the way the equations work out. And we would above here have the J pressure variables, and then would down here have these K values. The interface values I've put in the intermediate region here, and you get a kind of bandedness, you see, where you get zeros outside those main blocks. Can we figure that out from above? Let's see, this first equation, Hj, Pj, all right, that's this term times this one, and then Hjc, Pjc, Hjc, Pjc, still okay. And then from the right side, if we borrow the term here, G, Jc, V, Jc, that is this fellow here. The superscript is left off of these coupling terms here because they belong to both regions now, not strictly a J or a K region. And then the Gj, Vj is left on the right side over here with the 0. And so I think the first equation you've seen holds true, and you can follow through with the second one. And the point is then that you get this kind of a banding in which you've got large blocks of matrices in the interior. But that is a favorable effect, and I'm going to show on the next slide how it could help you on a sort of a tube-like body. The zoning approach is necessary when you have actually two fluid regions that you're interested in, and then it can arbitrarily be used in a problem where it can artificially represent a partitioning of your structural problem. For instance, if you had the interior problem here of this slender tube, and without zoning, you'd have to mesh the surface of the whole body in some pattern, and you'd end up with a certain number of nodes. An alternate way would be to create these artificial interior surfaces, just cuts through the diameter like this. And then you would only have to mesh 1/3, say, of the tube at a time, plus the artificial surface. Then your next zone would be the comparable next section, and so on. Now, because you haven't added very much surface area here, the total wetted surface of this particular segment of the body, or this zone, wouldn't be as big at all as the original number of nodes needed in this larger wetted surface area. So it can be usefully used that way. Now you also can have exterior fields, but you can only have one infinite exterior field on this body. Why? Because you can't mesh the artificial division. Suppose you really were interested in exterior fields here, and you wanted to break it into 3. Then you, rather than this artificial interior surface, you'd be trying to define an increasingly large exterior surface and having to mesh it, and that isn't doable at the present time. To this point, we've been talking about getting n equations in n unknowns. And although we started with a data recovery point that was in general off the vibrating surface, in order to get n equations in n unknowns, we evaluated that pressure at the same nodes that we were placing the sources. Now, though, sort of as a data recovery process, we'd also like to get pressures that really are out in the field of interest, whether it's an external or an internal field. Here I show a figure of an external recovery point here, and in order to do that calculation you have to use a formula shown here, the very formula we had before, but it does involve a lot of geometry on finding the pressures then at this data recovery point. Notice that this is a forward process, it's not an inverse process, and although this is a complicated calculation, you don't get caught on all the simultaneous equations that you had before. But it is viewed as a part of the expense of the solution, so data recovery here at points away from the surface does involve a separate calculation. That's a bit reminiscent of recovering internal stresses in structural finite elements after you have found the nodal values, and philosophically it's quite similar here. Often this is organized so that your recovery data points lie on some sort of a viewing surface, such as a plane or a cylinder or a sphere, and that has been automated very well within some of the commercial codes. In Comet Vision, which is the pre- and post-processor, for instance, those kinds of viewing surfaces are automatically constructed and meshed, so it's really a help. And then the colored figures that result are really glorious when you see the pressure levels on those viewing surfaces. Problem 1 in our problem session will be a check on the fundamental solution in 3 dimensions to make sure that it satisfies the Helmholtz equation. We're interested in the 3D fundamental solution. We're going to check it in the Helmholtz equation away from the point source. The best way to do this is to use spherical coordinates, because that will eliminate 2 of the 3 variables in a 3-dimensional space. So our solution then comes about by looking at an outward traveling spherical wave. The Laplacian operator reduces to these 2 terms involving only the radial coordinate. Those terms appear in the Helmholtz equation here as the acoustic pressure terms, and then we also have this inertial term. The question is, of course, whether that really is 0 if we put in the special case where the pressure field phi is given by psi. The fundamental solution, when it was given nominally in Cartesian coordinates, albeit with a vector symbol r, involved absolute value signs. But if you go into spherical coordinates, then since the radial dimension is always positive, you don't have to worry about that. I'll rewrite the fundamental solution here then, and without any absolute values, and that makes it a lot easier for us. If we propose that psi is a solution to that Helmholtz equation in spherical coordinates, we just put it in like this, and now I need 2 derivatives here on the left, and I've carried those out. It's moderately complicated because of the occurrence of the independent variable in the numerator and the denominator both. Those terms are shown here. Then the second derivative is taken and expands that first square bracketed term into 4, coming up with this final expression. I'm canceling the terms in pairs. These are 2 red arrows that cancel, the 2 blue arrows cancel, and then the 3 green arrows cancel. And so you see that this indeed is true. So it's easy to work the problem backwards and show that the fundamental solution indeed does satisfy the Helmholtz equation. And that's a far easier thing to do in spherical coordinates than to do it in Cartesian coordinates, I can tell you, because taking derivatives with absolute values and strange things like that is not much fun. Lamb, in his book Hydrodynamics, showed an alternate way to look at this problem. He showed that the Helmholtz equation simplifies by using the variable r phi instead of r alone. By recovering the time dependence in this harmonic oscillation, you would get this term here. That is the wave equation and admits general solutions shown below. And in turn, the term right here, the outward traveling wave, is exactly what you get when you take our form for psi of r to be the exponential form that it is, and then put in the time dependence e to the I omega t. So you can show that that is a solution. Well, that completes our lecture, and our next lecture will give some examples of the direct boundary element method in acoustics.